Revolutionizing the way we live, work, and interact with the world are the two dynamic and hardened fields of mechanical and mechatronics engineering. But amongst the rapidly accelerating robotic systems and earth-shattering new rocket engines, there are still many important questions left unanswered. Which is a superior career outlook? Which has a more engaging curriculum? And what do these engineers actually do? Today, we're going through the weeds to reveal all of this and more in a full throttle across comparison. Whether you're a student on the brink of choosing your major, a professional contemplating a shift, or simply an engineering hobbyist, watch closely as we explore the basics and the lesser-known intricacies that differentiate these fields' careers, applications, curriculum, and yes, of course, their pay. I'm Engineer Joe. Welcome to Engineering Insiders. Now, engineering is an ever-evolving landscape in which technology and creativity continue to push the boundaries of what's humanly possible. In this landscape stand two sought-after critical pillars, mechatronics and mechanical engineering. But what's the real difference between them, and what do the engineers actually do? Well, mechatronics is a newer field, a mix of mechanics, electronics, and computing that serves as the backbone of the automated systems that power our daily lives. From the robotic arms assembling every device in your life to the autonomous systems magically guiding vehicles, mechatronics engineers have their hands everywhere. In a nutshell, these engineers use their programming and electronic skills to connect various electrical controllers to all types of mechanical systems to power and manipulate them. The scope and career growth here is explosive, as these engineers could craft every aspect of groundbreaking new products that launch startups or automating processes and enhancing product functionalities in the largest of companies. Now, mechanical engineering, on the other hand, is an older field, debatably one of the oldest. It's the art and science of designing, analyzing, and manufacturing everything from small individual parts like microscale sensors to the largest tanker ships and spacecraft that you could possibly imagine. Ditching much, but not all, of the electronics and programming that we saw in mechatronics, mechanical engineers focus the principles of force, energy, and motion to design everything from car suspension to prosthetic arms to our rugged and versatile Mars rovers. They accomplish these feats by regularly modeling and simulating mechanical systems, manufacturing and testing them, and analyzing failures. This field continues to be indispensable in automotive, aerospace, energy, and manufacturing sectors and isn't going anywhere anytime soon. Actually, the demand for mechanical engineers is expected to skyrocket in the next decade as new technology in material science, renewable energy, bioengineering, and many other fields take shape. Both of these two fields offer a lucrative outlet for creativity and innovation, but the choice between them hinges on your passion for integrating circuits and programming with mechanical systems versus mastering the mechanics of movement and energy. But if you were to ever truly understand which is the perfect one for you, we must dive into the roots of the field, the curriculum that catapults these engineers into their desirable careers. Now, the choice between these two isn't just about which career sounds cooler. It's about what you'll learn on the journey there and the resume skills that you'll apply for the rest of your career. So let's check it out. And remember, if you learned anything in this video, please drop a like and consider subscribing. It's free and really helps us out. Now let's see what these expensive degrees have to offer. Starting with mechatronics, this field is a Swiss Army knife. Dangerous enough to tactically approach any problem within the software, electrical, or mechanical engineering spaces. As you might be able to guess, the curriculum reflects this with a ton of diverse courses. Of course, they have their standard year of physics and 2+ years of math, mainly calculus, to attend as well. But getting into the juicy classes, first we have circuits. These courses solidify understandings of resistors, capacitors, and inductors, then move on to more advanced devices, like active transistors and diodes. Without this circuitry, controlling motors and other crucial mechanisms that actually get your machine to move would be impossible. And just so you know, building a robot that doesn't move means you probably didn't build a very good robot. In the software curriculum, students take essentials of computer organization, networking, and embedded software, which provide the concepts and practices for designing and sustaining intricate computer systems. To picture this, consider a sophisticated manufacturing line with hundreds of robots, each itself with many configurations. You can bet your bottom dollar that a bulletproof computer organization and networking understanding is necessary to successfully integrate them all together and maximize efficiency along the way. On a smaller scale, they also learn the software skills to literally create small, compact, specialized computers, like the programming that ensures each processor in a Tesla sets itself up correctly to interpret the road's real-time data, a process that needs to happen flawlessly on every start of the engine. But all of that is of no use to our mechatronics engineers without mechanics. In the mechanical part of their mechatronics degree, students start with statics, dynamics, and fluids to understand the physics behind the stationary, moving, and liquid and gaseous objects and systems. This provides insight into the forces of trusses holding up bridges, translating forces of crank and slider mechanisms, and the thermodynamic and aerodynamic properties of things like cool air moving through the entire Burj Khalifa, or the aerodynamics of the X-59 that travels literally 1,000 miles an hour. As you can imagine, the mechanical degree is very similar to this mechanics focus of the mechatronics degree, but explores much more in depth of each iceberg, and even further onto the advanced strength of materials, applications into specific sectors like aerospace, and more reps with mechanical CAD modeling and simulations. So both fields demand a strong aptitude for mathematics and physics, but apply them in different ways. Where mechatronics focuses on the control of mechanical systems with electronics and programming, mechanical degrees fully submerges into mechanical design and analysis. But regardless of which field students choose, they emerge as critical thinkers and problem solvers, which is good because we have a problem. When nearing the end of the degree, which career path should you choose to concentrate in? And how do you maximize your chances of landing the highest paying, best job possible? Well, to set yourself up for realizing your dream job, check out our proven best path for getting hired when you're done here, and subscribe for the upcoming boatload of other tried and true insider tips for maximizing your potential. But for the concentration problem, let's explore some career options, and make sure to stay tuned because their stacked pay is coming right after. First, mechatronics engineers are somewhat prepared to pivot into anything in the greater mechanical, electrical, or software landscapes, but are very well prepared for a smaller batch of fields within them. One of them being embedded systems engineering, which leans further into the electrical and software sides of things to basically design your own small computers, just like the Tesla computers that interpret sensor data and decide how to act on the information. They can also work in robotics fields, making control systems, just like that decision-making system in the Tesla. These are found in any type of robot, from new age chef robots that cook and clean for you, to Boston Dynamics' ever-evolving aerobatics beasts. But more broadly, they're actually well suited to design these control systems as control engineers for anything in the greater defense, manufacturing, aerospace, automotive, renewable energy, IoT, medical devices, biomechanics. Really any design you can think of that uses a sensor to processor to action control system can be heavily carried by mechatronics engineers. So to put a bow on this, if you were to focus software courses in your mechatronics degree, you really could go on to a fancy software role at any of the largest tech companies, and the same optionality goes to mechanical, electrical, and computer engineering roles if you wanted to focus them. But the more mechatronics roles heavily involve control systems, which take a few pages from each of the above fields and use them together for a huge number of applications. Now that was mechatronics, let's explore the mechanical career options out there. The big ones are HVAC, manufacturing, aerospace, and you guessed it, mechatronics. First, HVAC engineers use thermo and fluid dynamics to design heating, ventilation, and air conditioning for every modern car, plane, spaceship, and building. They analyze airflow patterns, pressure drops, heat transfers, and behaviors of fluids at different temperatures so that you and I can sit comfortably while doing our engineering work. But manufacturing engineers are very different, dealing with everything involving turning raw materials into goods, like the processes, machines, and tools that turn epoxy resin, copper, and silkscreen ink into individualized circuit boards that power our daily devices. You can imagine that integrating all of this very specific machinery, processes, and materials to manufacture circuit boards is a very niche system, which is why good manufacturing engineers are so sought after. This entire manufacturing process applies to basically every product you've ever known, from processed candy and plush toys to satellites and skyscrapers. Speaking of satellites, up next we have aerospace engineering. These engineers design, troubleshoot, and bring to life all the spacecraft leaving the atmosphere and Earthcraft that need to take aerodynamics into account. You can find them modeling and simulating aircraft wings, exercising the thermodynamics in new jet engines, structurally designing the physical bodies for all of these crafts, and more. Now speaking of structures, mechanical engineers can also become structural engineers, considering the stress, strain, vibration, and forces that everything from helicopters to prosthetic arms will take on throughout their lifetime. And the last one we'll touch on is working in the energy sector, designing solar panels, checking out the aerodynamics of wind turbines, looking at the mechanics and machines of oil drilling, or designing the imperative structures and materials that go into keeping nuclear power plants safe. So basically anything that involves materials, manufacturing, mechanics, structures, aerodynamics, or HVAC. So basically everything ever. You can find mechanical engineers designing, optimizing, and troubleshooting them. Now make sure to subscribe for more info on mechatronics and mechanical subfields, because now we finally get to the part that you've all been waiting for. Dollar signs. Mechanical engineers rake in an average of $101,000 a year in the US according to the National Bureau of Labor Statistics, whereas mechatronics engineers with their added specialties come out to right around $110,000 a year salaried. But that's just it. This is only salary. If you factor in average bonuses at around $10K a year, these numbers boost to around $111,000 and $120,000 a year. But we can't just leave you there. We know that these two fields have a ton of career options. How much do those make? Well, we added those here for you too. Now, if you want to find out why students are piling up in droves to choose mechatronics engineering over any other major, check this video out. And if you're still here, make sure to like and subscribe or be cursed with unpaid internship offers forever. Thanks for watching and happy engineering, everybody.